Welcome, everyone. Let's jump right into today's explainer on the IEC 611313 standard. As diploma students gearing up for the real world, getting a solid grip on this global language of industrial automation is a massive step in your professional journey.
Here is our agenda for today. We'll kick things off with an introduction to the IEC 6131-3 standard, move into the basic elements and structure, and then explore graphical programming languages, followed by textual programming languages. After that, we'll check out the sequential function chart, and finally look at real-world industrial applications.
Section 1. Introduction to the IEC 611361-3 standard, the global standard for PLCs.
Imagine walking onto a factory floor where every single machine speaks a completely different language. Total chaos, right? Well, that was exactly what the automation landscape looked like before this standard came along. Every vendor had their own proprietary code. But in December 1993, the International Electrotechnical Commission published this standard, and it totally unified the syntax and semantics for the whole industry. It's constantly evolving, too, with a modernized 4th edition rolling out in 2025.
Section 2. Basic Elements and Structure, Building the Foundation.
Before you even think about writing a single line of code, we have to talk about data typing. It's an absolute lifesaver for preventing silly early errors, like, accidentally trying to divide a calendar date by an integer. The standard lays out these universal data types you'll use everywhere. For instance, bool is just a 1-bit string, a simple 0 or 1. Int is your signed integer, taking up 2 bytes, and real handles your floating point numbers, taking up 4 bytes.
Now, think of the software model like a set of Russian nesting dolls. It brilliantly organizes the whole control system. At the very top, your overall system is the configuration. Crack that open, and inside you have your processing resources. Those resources run specific tasks, and those tasks are what actually control the execution of your programs. It's this exact modular structure that makes complex distributed factory networks possible today. When you're actually sitting down to build these applications, the standard essentially gives you 2 ways to tackle it. The top-down approach means you look at the entire application from a bird's-eye view and chop it up into smaller, manageable subparts. On the flip side, the bottom-up approach has you starting small, building up from custom functions and combining them until you've built the whole system. Honestly, you'll definitely use both methods in your careers, depending entirely on what the project demands.
Section 3. Graphical Programming Languages, Visual Programming Tools. First up is the ladder diagram, or LD. This one has deep roots in the US and is totally based on the look of old-school physical relay logic hardware. Because it basically looks just like a traditional electrical circuit, it is incredibly intuitive for electricians and technicians who are out there upgrading older hardwired systems. It's fundamentally a rule-based language, and it literally looks like a ladder. You've got 2 vertical power rails and a bunch of horizontal rungs connecting them. Every single rung is a rule, and the PLC just reads down those rungs one by one in a crazy fast continuous loop. It effectively wipes out the need to build those massive, bulky relay cabinets. Our second graphical option is the Function Block Diagram, or FBD. This language maps out the functions between inputs and outputs using interconnected blocks. It is massively popular in the process automation industry, and visually it's going to remind you a lot of reading an electronic circuit diagram. Now, what's really fascinating here is how FBD takes incredibly complex algorithms and wraps them up into neat, reusable boxes. Data always flows left to right, inputs to outputs. The complicated math happening inside the block is totally hidden from you, kind of like a physical computer chip. That makes them perfect for dropping into critical tasks like PID control loops, all while strictly enforcing those data type connections we talked about earlier so nothing crashes.
Section 4. Textual Programming Languages, Code-Based Automation.
All right, shifting gears from visual to text. The main one you need to know is structured text, or ST. This is a high-level, block-structured language that looks a lot like Pascal. For those of you who already like computer science or traditional coding, you're going to find ST super intuitive and a lot faster to write than dragging and dropping graphical blocks.
The real superpower of structured text is right there in the name. It's structure. If you're working on a task that requires heavy math, totally custom algorithms, or really intricate decision-making, ST is absolutely your best friend. You get to use all the classic coding operations you might already know, like iterative loops and conditional if-then-else statements. Just for some quick historical context, we should mention instruction list, or IL. It's a very low-level text language that runs line by line, almost exactly like assembly code. You don't need to worry about it too much, though, because it's obsolete now. It was deprecated back in 2013 and officially scrubbed from the 2025 standard as the entire industry moves toward higher-level programming.
Section 5. Sequential function chart, orchestrating the process. So how do we organize all these different languages in a big project? That is exactly where the sequential function chart comes in. It acts like a high-level project manager. It takes a massive, complex process and breaks it down into simple steps. It then uses logic-based transitions to figure out exactly when to move from one step to the next. And because it allows multiple control flows to run parallel at the exact same time, it is an absolute game changer for complex batch manufacturing where a dozen things need to happen at once.
Section 6. Real-world industrial applications. Real-world implementation.
Okay, here is the absolute crucial point to take away from all this theory. All of these languages, they are completely interlinked. You could write the exact same piece of logic in any of them, and you can even mix and match them inside a single program. This means an old-school electrician and a fresh-out-of-college software engineer can actually collaborate, read the same overall program, and troubleshoot a machine together.
Let's ground this in reality for a second. Think about heavy-duty physical equipment, like these ABB total flow controllers. These robust industrial boxes are exactly what you're going to be working with out in the field. And what's running quietly inside them, keeping a massive factory from grinding to a halt? It's logic built entirely on the IEC 6113-3 standard we've been breaking down today.
For you guys, as diploma students stepping out into the workforce, learning this standard basically boils down to two words: vendor independence. Mastering this means you aren't stuck programming just one specific brand of hardware for the rest of your career. You can program systems from dozens of different vendors worldwide, which makes you incredibly valuable and seriously bulletproofs your resume in the job market.
To wrap up today's explainer, I want to leave you with a thought to chew on. With advanced concepts like object-oriented programming now being fully integrated into the standard's latest revisions, how are you going to use these cutting-edge tools to shape the future of smart manufacturing? Thank you so much for joining me today, and best of luck as you dive into the exciting world of industrial automation.